Welcome to this beginner's guide on working with rigid bodies and physics in Unity 3D using Visual Studio for C# scripting. Our goal is to empower you to create interactive game elements by applying realistic physics to your game objects. The Unity Physics Engine is a powerful tool, enabling objects to approximate universal forces like gravity, velocity, acceleration, and friction. It allows for a wide range of objects with various physical properties to interact dynamically within your scene. Let's begin by understanding rigid bodies, a fundamental component for physics simulation. A rigid body component is what enables game objects to be affected by physics properties, such as gravity. Key properties include mass, which determines how heavy the object is and influences its resistance to movement. Drag simulates air resistance, slowing down the object, while angular drag reduces rotational velocity. The use gravity option allows you to enable or disable the effects of gravity on the object. The is kinematic property makes an object a physics object but prevents direct physics application. This is suitable for moving platforms where you want the player to be moved by it physically without the platform spinning out of control. To control a rigid body via script, the primary methods are add force to apply forces and add torque to apply rotational forces. You access the rigid body component through code using getComponent rigid body. It's crucial to attach at least one collider to either the current object or its child objects for physics to work correctly. Additionally, the mass of the object cannot be zero for proper physics simulation. Next, let's delve into colliders, which define the physical shape of your game objects. Colliders are invisible components that define the shape of game objects for physical collisions. They don't need to match the game object's visual mesh exactly. Primitive collider types include box, sphere, and capsule colliders, which are highly efficient. For complex shapes, you can combine multiple primitive colliders or use mesh colliders. However, mesh colliders are computationally expensive. Using simpler, primitive colliders is generally more efficient. If a mesh collider is necessary, consider using a simplified mesh for better performance. Colliders trigger events when they touch or overlap, allowing you to respond to physical interactions. On-collision enter is called when two colliders begin to collide, specifically on the first frame of contact. On-collision stay is called every frame the colliders remain in contact. And on-collision exit is called when the colliders separate. Triggers are a special type of collider that detect when other colliders pass through them, initiating events without causing physical collisions. You enable the isTrigger property on the collider component to turn it into a trigger. OnTrigger enter is called when a collider enters the trigger zone. OnTrigger stay is called each frame a collider stays in the trigger zone. And OnTrigger exit is called when a collider exits the trigger zone. Remember, one of the objects involved needs a rigid body component for collision and trigger events to be detected. You can also use physics layers to group objects and optimize physics calculations, preventing unnecessary interactions. Now, let's explore physics materials, which fine-tune friction and bouncing effects during collisions. Physics materials allow you to adjust how objects behave when they collide. To create one, simply go to Assets, Create Physics Material in Unity. Dynamic friction controls friction when the object is moving. A value of 0 feels like ice, while 1 makes the object stop quickly. Static friction governs friction when the object is at rest. 0 means anything gets it going, while 1 requires a heavy push. Bounciness determines how bouncy the surface is, with 0 being no bounce and 1 being a full bounce without energy loss. Friction combined and bounce combined determine how these properties are combined when two objects collide. These options allow for nuanced interactions between different materials. Let's move on to basic physics interactions using C# in Visual Studio. Applying forces is straightforward with rigid body to add force to make a game object move. For example, RB.addForce can make an object jump. For collision detection, implement onCollision enter, onCollision stay, and onCollision exit functions. You can use collision.gameObject.tag to identify the specific object collided with. Here's an example. If the object collides with a floor, it could trigger a jump. For trigger events, implement onTriggerEnter, onTriggerStay, and onTriggerExit functions. Use other.gameObject getComponent T to access components of the other game object that entered the trigger. For instance, if a power-up component is detected, you can apply its effects. Finally, let's cover some helpful tips for optimizing your physics simulations. For performance improvements, simplify physics meshes and always prefer primitive colliders. Also, consider reducing the number of physics updates by increasing the fixed time step in the time manager. Utilize physics layers to optimize calculations by preventing unnecessary interactions between objects. Apply physics materials to colliders to precisely control friction and bounciness, enhancing realism in gameplay. Use the fast mid-phase option to skip generating resource-intensive archeries, improving performance. Additionally, offload mesh cooking to another thread using the C# job system to cook meshes on a different thread. Finally, employ non-allocating queries for physics checks, as queries returning multiple objects can allocate memory on the managed heap. By understanding and applying these concepts, you can create dynamic and engaging physics-driven experiences in your Unity projects. We hope this guide has provided a solid foundation for your journey into Unity physics.